Hello, I'm John Benson, and I am a math teacher, and I would like to talk to you today about numbers. So first of all, where do we think numbers came from? Well, it's likely that people had to keep track of things, like their sheep. And so what they would do is take a pile of stones, and every time a sheep went out into the field, they'd move a stone from here over to here. And so the pile of stones over here would represent how many sheep there were out in the field. And then at the end of the day, they would move the stones back, and when there were no stones left, they'd know that all the sheep were back. And if there were some stones still left, then they knew they still had to go and take a look for some sheep. As things became more complicated, as there became more and more people and they were doing more and more things, it became clear that just having piles of stones wasn't going to work, that they had to have a way to keep track. And the first thing probably was just to make little slashes. So each one of these lines would represent a stone. Well, but that became pretty complicated, and so what they would do is, after they'd get to a certain point, they'd make a mark, and that would help them to group things in different ways, and that's how they would count things. As society became more and more complicated, it was useful to give these names numbers. And so what they did was, because of our 10 fingers, they came up with 1, 2, 3, 4, 5, 6, 7, 8, 9, and then 10. Well, they wanted a better way to do that. So what they did was to invent the number 0 so that this 10 could become the next set, and so on. And you know how those numbers work. But inventing the number 0 was kind of interesting. These numbers here are called the counting numbers. When you add 0, you get the whole numbers. Now, the set 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, or 1, 2, 3, 4, 5, 6, 7, 8, both have several properties. And that is, if we take any collection of them, let's say we take a set of them, a finite set of them, we just collect some, there's always going to be a smallest one, there's always going to be a largest one. And then there will be some in between, we may have skipped some. The other thing is that every number has a neighbor. That is a number right next to it, except 0 has only 1. Every other number has 2 neighbors. So those are some of the properties of the counting numbers and the whole numbers. As time went on, it became helpful, useful, important to learn how to do things with these numbers so they could keep track of large numbers of things. As you might imagine, the first thing they learned to do was to add them. Adding was fairly simple. You simply counted up how many sticks you had in one, how many sticks you had in the other. You put that all together, and that told you how many that you had. So you had, and then the symbol for it was that. And so you had things like 3 plus 5 equals 8. And you learned how to do addition. It turns out that you can add any of these numbers. One of them has a very particular property, and that is 0 plus any number is equal to the number. The number doesn't get bigger or smaller, it just stays the same. So 0 is a very, very special number for that reason. Now, we can do this with any number we want, and we learned that addition is very useful. It helps us keep track of things. But, and this is part of the story of numbers, and that is whenever you do something, that is, we do addition, we also want to learn how to undo. And as you well know, that's subtraction. So the problem might very well look like 7 plus what equals 11? And we want that number. That number is going to be 11 minus 7. And so now we have a new operation, subtraction. The issue is that now that we're subtracting, we have to find the properties of subtraction. With addition, it was clear that we could take any two numbers and add them. With subtraction, we can take any two numbers and subtract them, but there's a problem in some cases. I can do 8 minus 3 and get 5, but I can't do 3 minus 8. And you might have been told in school when you were first learning, maybe not, but you might have been told that you can't do 3 minus 8. You can't subtract a bigger number from a smaller number. And that is true as long as the only numbers that you know are the whole numbers. And so the story of mathematics is that when we find something we can't do, we fix that by inventing something else. And so what we're going to do is to add the negatives. And when we do that, that will give us what we call the integers. So that's like -6, -5, -4, -3, -2, -1, 0, 1, 2, and so on. And then we have to learn how to do addition and subtraction with these numbers, which we do. And we make sure that the rules still hold. And then we look at the list and we say that any set is still going to have a smallest number and a largest number as long as it's finite. So if I say I want all of the numbers n which are bigger than -3 and less than 5, then there's an answer to that. I can go to the list and I can look and I can write them. -2, -1, 0, 1, 2, 3, 4. And those are all of those numbers between any two numbers. And I can do addition with them, I can do subtraction with them. Takes a little work to figure out how to do subtraction, but it's not too bad. You just pretend like you're doing addition. And so there we have it. We have the integers. And so now it's time to do some more complicated mathematics. And what we're going to do is repeated addition. In other words, I want to do 7 times 5. I'm going to call that multiplication. That means I want to take 5 7 times. And because I can do all the addition, I can do all the multiplication. Everything is good. I guess I should write this way instead. So we now have a new operation, and we have to learn all of its properties. And all of that comes down to what you did, I don't know, early in school. You learned your times tables. And it was important to learn that so that you could do more complicated multiplication. But then we have to undo multiplication, because whatever we do, we have to undo. And when we undo multiplication, Well, so for example, like 3 times what number equals 18? Well, then that would be 18 divided by 3, and that would give us 6. I prefer to write that this way. You may prefer to divide it this way. There's advantages to all of them. But anyway, so now we have division. And as with the other operations that we've learned, we need to look at all of the properties of division. The first question always is, are there division problems that we can't do? And this time, we have a big answer. If we take any number and we try to divide it by 0 and get a different number, we have a problem. Because if n divided by 0 is m, that means that n is equal to 0 times m. But 0 times anything has to be 0. And so that means that the only division problem we can do with 0 is 0 divided by 0. But in fact, we can't even do that because we don't know whether 0 divided by 0 is 0, because whenever you divide anything, divide 0 by anything, you have to get 0, or is 0 divided by 0 equal to 1, because anytime you divide a number by itself, you get 1. And the answer to that question is, well, that means we're just never going to divide by 0 now. We're going to forget about that, never divide by 0. But you can divide by any other number. You can divide anything by any other number. When you learn some advanced mathematics, you will find ways to sort of divide by 0. It's very important that we learn to divide by 0, but we can't ever really divide by 0. But that's another story for another day. Okay, so now what we'd like to do is to take a look at division. And as with subtraction, we realize that we have some serious problems. We can do 8 divided by 2, and we get 4. But if we do 2 divided by 8, then we don't know what to do, because there aren't 8's too big to fit into the 2's. So you can't say how many 8's does it take to get 2. Still, if we're going to do this division thing, we would like to be able to do it with all of the numbers. So we're going to invent a new kind of number. You probably know it as a fraction. I would like to call it a rational number. An irrational number is simply the number that's created by taking one integer, another integer, and dividing them, remembering that we can't let b be 0. Now, you have spent or will spend many years in school learning how to do addition, subtraction, multiplication, and division with these numbers. But there are also some interesting things about them. Let's look at the problem that we had before. I'll change it a little bit. Let's say we say 2 is less than x is less than 5. Now, when we had the integers, the answer would be 3 and 4. But now that we have these rational numbers, we have a very serious problem. And that is, we can't list them, because there's no smallest one. There's no largest one. And between any two, there's infinitely many numbers. And we can do that by just averaging them. If you take two numbers, a over b and c over d, and you add them and divide by 2, you get a number which is between a over b and c over d. So I can always find a number that's between two rational numbers, and I can keep doing that and keep doing that and keep doing that. So what happens is that when we get the rational numbers, we lose something very important about less than or equal to, and we can't find a smallest one. And we get many more. There's infinitely many of these things in any set that we pick where we include all of the rational numbers. Nevertheless, the rational numbers are very important to us. So let's go on. One of the things that we would like to think about is repeated multiplication. You may know it as powers. You may have called it exponents. But what it looks like is if we take something like 3 to the 5th, it means we're going to multiply 3 5 times. Now, you'll notice that this is a little bit like multiplication. If we take 3 times 5, we add 5 3 times, or we add 3 5 times. We take repeated multiplication, it means we're going to multiply 3 5 times. So, one of the nice things about this is, if I take 3 to the 5th times 3 to the 4th, I'm going to get 3 to the 9th, because there's 5 here, and then there would be 4. There'd be 4 there. And so altogether, that would give me 9 3s. And so this exponent multiplication, one adds the exponents. Likewise, if I wanted to do 3 to the 5th 4 times, that would be 3 to the 5th times 3 to the 5th times 3 to the 5th times 3 to the 5th, which would be 3 to the 20th. And so I would multiply those things in order to do repeated multiplication. Now, the interesting thing is what happens if we use a fraction as our exponent. What happens if we do 3 to the 1/2? I take half of 3? Well, I don't think so. That's not even a number there, so we're not going to do that. What does 3 to the 1/2 mean? Well, we're going to look at this property in order to make sense out of it, because it means 3 to the 1/2 times 3 to the 1/2 has got to be 3. So that means that 3 to the 1/2 has got to be the square root of 3, or the number that you have to square to get 3. What is the number that you have to square to get 3? Well, we've got a problem now, because that number doesn't exist. Because if we try to take the square root of 3 equals a over b, then that means the square root of 3 times b is equal to a. And that means 3b squared equals a squared. But then a squared is a multiple of 3. So a squared equals 3 times k. But if a squared equals 3k, that means a is equal to 3 times something, because if the square of a number is a multiple of 3, the number has to be a multiple of 3. So that means the square root of 3 equals 3j over b, or 3b squared equals 9j squared, or b squared equals 3j squared, and therefore b is a multiple of 3. But a is a multiple of 3, b is a multiple of 3, So that means that the fraction a over b can't ever be reduced. It's equal to 3j over 3k, and no matter what we do, we keep getting these 3's, and that's impossible. We can always write the fraction in lowest terms. Therefore, we can't ever write the square root of a number as a ratio of rationals, and that means we need new numbers. And those are going to be called the irrationals. Now, one of the things about rational numbers is because rational numbers can be written as the form a over b, then they can be written as decimal fractions that either end or repeat. Think about 3/7. So the way we convert that into a decimal is to divide 7 into 3. And this is going to be 428,571, again and again and again and again and again repeating. And you see what happened is when we did the division, we eventually used up all the remainders of 7. 2, 6, 4, 5, 1, 3. That's all of them. So we had to start using one of them again, and as soon as we got one of them again, then we got to repeat. Now you can see that it doesn't matter whether we use 7 or whatever number we use there, we're always going to get a repeat. So anytime we take a number like a over b, the number is going to repeat. That means that a number like the square root of 2 will not repeat. Because if it did, we could write it as a rational number. And that means that we have a set of new numbers. We'll call these the irrationals, and I'm going to label them as the non-repeating decimal numbers. And so we have some of these things, like the square root of 2 is one of them. Now we pretty much got what we call the real numbers. And those are the numbers that we know about. So let's do some more arithmetic. One of the things that we want to learn to do is repeated multiplication. And so we want to take 2 to the third. We want to take 2 to the 1/2. And that gives us the square root of 2, and that gives us this irrational number. And we want to take 2 to the negative 3. Well, how do we make sense out of that? Well, we say, what do I multiply 2 to the negative 3 by to get 2 to the 0? Because I know that 2 to the 0 is 1. Because 2 to the 0 is 2 to the a over 2 to the a minus a is 0, and that's a number divided by itself is always 1. Okay, so what does this have to be? Well, it appears as though x is going to have to be 3. So that means that 2 to the negative 3 times 2 to the 3 is 1. So 2 to the negative 3 has to be 1 over 2 to the 3. And so indeed, we want to say 2 to the negative 1 is 1 over 2 to the 1. So what we say is that a negative number takes the reciprocal of a number. So like 3/4 to the negative 1 is going to be 4/3. All right, so we have another big question, and that is, what happens if I take a negative number to the 1/2? In other words, what number, when multiplied by itself, gives me -2? And you have learned that there can't be any such number because a negative times a negative is positive, and a positive times a positive is positive. And so x squared must be greater than or equal to 0. But -2 isn't. So once more, we have encountered the problem that we can't do. And so once more, we have to invent a new kind of number. We're going to invent what was called, for strange reasons, the imaginary numbers, the square root of -2. And in fact, we're going to write that as the square root of -1 times the square root of 2. And we're going to say that the square root of -1 is going to be written as I. And that is just a way of making life simpler. If we put some more things together with this, we get the complex numbers, and those are numbers of the form a plus bi. And then you learn to do arithmetic with a plus bi. But I would like to raise a few questions. And that is I plus 1 bigger than 0? Or is I plus 1 less than 0? It's pretty clear that it's not equal to 0, because if we multiply it by something, we don't get 0. But is it bigger than 0 or less than 0? Well, what about I, right itself? Is I bigger than 0? Or is I less than 0? If I is bigger than 0, then I times I would be bigger than 0. But I times I is -1. So that's false. Is I less than 0? Well, if we multiply two negative numbers, we get a positive number. So the same thing would be true. But we know that that's false as well. So we have a number, I, which is neither greater than 0, nor is it less than 0. And so we need to find a new way to compare these things. And that is a quest. That's something that you'll learn about someday. You probably haven't learned about it yet. We also want to worry about what happens if we take 1 and raise it to the I power. Or what about 2 plus I to the 1 plus I power? Or any complex number raised to any complex power. How do we make sense out of that? We can take a complex number to a real power because we know how to repeat multiply. But how do we take something to a complex power? And that, again, is something for your advanced studies. But I would encourage you right now to think about it. What could it possibly be? And remember, whatever it is, it has to make sense with the mathematics that we already know. Thank you.